Let's continue with grasping complexity and now look at consequences of complexity. Again, always remember we are trying to deal with the human environment systems, and here in Approaching the World, the second section of the book, we are heading towards how to represent the human environment systems and what kind of reductionist approach we can take to represent the system or the part of the system we want to look at, because there are many elements, there are many connected behaviors, cascades, feedbacks, and it's a tremendously complex system, and yet we want to understand it by somehow reducing it into some manageable system. The manifestations of complexity introduced above have real consequences on our ability to understand, explain, and improve phenomena and problems concerning risk and resilience. As already alluded to in the introduction to this chapter, complexity is not only a fundamental challenge in itself, but also exacerbates the other three specified in this book. Complexity escalates uncertainty as feedback disproportionately between cause and effect, emergence, and downward causation introduce inherent unpredictability and undermine our ability to grasp how our systems of interest work. So it has uncertainty that can get amplified by complexity of the system, of course, as has feedbacks which can in fact add to this uncertainty and the emergent properties. So that comes also from disproportionality between the cause and effect. So amplifications and damping can happen within the system, and then you have downward causations which can introduce inherent unpredictability and undermine our ability to grasp even how the systems actually work. Complexity is also the root cause of the dynamic character, since far from the equilibrium dynamics and the resulting self-organization and adaptation, as well as path dependence and lock-in effects, both cause and constrain change. Finally, complexity engenders ambiguity, as the sheer unknowability of complex systems opens up multiple interpretations. However, this does not mean that we cannot know anything about these systems, nor that their complexity completely incapacitates us. Outcomes are still bounded even though they are not predictable. So we looked at the chaotic system with its strange attractors, and similarly you can have a complex system that is still somehow bounded. There's many dynamic system terminologies that I won't get into. For example, nobody can predict the Chad or blizzard in nobody can predict the weather 6 months from now, but I know that there will be no category 5 cyclone in Chad, which is in Western Africa, far away from the coast, and cyclones have never gone there in our history, but with warming you never know. Or blizzard in Singapore, which is basically on the equator and cannot get snow as far as we know. So we'll look at this in a minute. That said, there are other consequences of complexity, often closely linked to the four fundamental challenges just mentioned, that require attention if we are to move forward, especially since complexity requires and enables profound changes in our policy making and practices. So it's a matter of risk perception. So it is a complex and uncertain and ambiguous system, but we know that there are risks nonetheless, and we have to prepare somehow. So something is better than nothing is not a good philosophy, but we have to say everything depends on everything, but make a decision somehow. So Singapore has typically tropical climate with the lowest recorded temperature of 19.4 degrees centigrade, so nowhere near something that can lead to a blizzard anytime soon. So the requisite rationality then for dealing with complexity, the most fundamental consequence of complexity is requisite rationality. If the system of interest is complex, it matters little how hard we try to understand, explain, or improve it by dividing it into parts and studying or addressing each part in isolation. Such a reductionist approach may work for simple or complicated systems, as we saw before, but it should be clear now that it is inappropriate for complex systems to deal with this simplistic reductionist approaches based on how you did it. There are three primary reasons for this. The first is obviously related to emergence, resulting in observed properties of the system that simply cannot be reduced to properties of its elements. You cannot think of the climate system as just based on land-atmosphere interactions or ocean-atmosphere interactions or without the glaciers and so on, because at some time scale they are all part of the emergent system and its complexity. Secondly, the state of anything in a complex system depends on many other things, hampering all attempts to grasp or address even a single element or issue in isolation. The third reason for the inappropriateness of reductionist approaches to complex systems is related to the assumption of ceteris paribus, that all elements that are not explicitly included stay the same over time. It's kind of like a partial differential equations where you hold one variable constant and differentiate with respect to other variables, and the variable you have constant has to remain throughout your analysis. So that's ceteris paribus, all else being the same. This assumption clearly does not hold for complex systems, since the rich dynamic and non-linear interactions between elements preclude attempts to keep them constant. It all leads to the absolute necessity of relationality, the perspective that nothing important in the world exists in isolation, and of paying serious attention to the effects of relations on the effectiveness of policies and practices for safety and sustainability. Unfortunately, there are countless examples of policymakers and practitioners ignoring interactions, focusing on particular and often somewhat arbitrary cherry-picked elements or issues, and still expecting results without ever considering what else is needed. We also tend to ignore complexity when we attempt to explain unexpected events. Right? Something happens and then you try to retrofit answer to it, which will be basically some kind of a consistency of explanation rather than real causation. So this is how you can think of it. When we are faced with unexpected occurrences, especially when they have catastrophic results, we tend to ascribe their cause a rare combination of unlikely circumstances. When we have to explain the crash of the stock market, an earthquake, or the sudden outbreak of political violence, we try to find a number of factors that combined to cause it, often with the hope of showing that the chances of the same combination of factors occurring again are slim. This kind of analysis, however, is the result of trying to explain the behavior of large complex systems by extrapolating from the behavior of small simple systems. Unfortunately, this extrapolation fails. Okay, so we talked about this in terms of the explanations for things that happened. So sign of commemorating the 3 Mile Island nuclear accident 1979, where combination of human failures and reactor failures and so on combined. But we'll come back and look at how complexity can produce a surprise. Right? You expect that complexity with all those emergent properties and kind of disproportionate cause and effect kind of relations and internal feedbacks and cascades, there will be surprises. And when we say these events like the stock market earthquake and sudden outbreak of political violence, they are often surprises, even though we go back and try to fit known factors to explain why these events happened, even though we didn't expect them, we didn't predict them, and we cannot even say when it may happen again. Okay, so let's meet in the next podcast.